Welcome to the third video on the first module semiconductors. So in this video we will be discussing about metals, semiconductors, insulators, what is direct and indirect gap semiconductors. We know that every solid has its own characteristics energy band structure. The variation in the band structure is responsible for the wide range of electrical characteristics observed in the various materials. As we discussed in the previous video, the silicon band structure consists of valence band, conduction band and a band gap or forbidden energy gap. Here, the electronic configuration results in a fully occupied valence band followed by the completely empty conduction band. So this gives a good picture of why a silicon in the diamond lattice is a good insulator. To reach such a conclusion, we must consider the property of a completely filled and completely empty energy band in the current conduction process. The electrons will experience an acceleration in an applied electric field and then they will be able to move to the new energy state. For example, if relatively few electrons reside in an otherwise empty band, ample unoccupied states are available into which the electrons can move. On the other hand, the silicon band structure is such that the valence band is completely filled at 0 degree Kelvin and the conduction band is empty. There can be no charge transport within the valence band since there is no empty states are available into which the electrons can move. There are no electrons in the conduction band, so no charge transport takes place there either. Thus, silicon at 0 Kelvin has a high resistivity typical of insulators. Semiconductor material at 0 degree Kelvin have basically the same structure as insulators, a filled valence band separated from an empty conduction band by a band gap containing no allowed energy state. The difference lies in the size of the band gap. So in this video, we will be discussing based on how the band gap, how the solids are classified as metals, semiconductors and insulators. So in this slide, we will be discussing about what is a metal. Consider a metal with a half-filled conduction band, that is a T is equal to 0 degree. As shown in the figure, here we will be having the completely filled valence band and the conduction band is partially filled. Partially filled in the sense there are some free electrons which will be involved in the current conduction. So the conduction band will be having the empty state, that is the white part of this will be the empty state. So the electrons which are present in the conduction band it will be having a plenty of free state or allowed state which the electrons can move. This type of solid would behave as a conductor and metals are the example for this. So in the next case, we will be considering insulators. Consider a solid with an empty conduction band. So here in this figure we can see that the valence band is completely filled whereas the conduction band is completely empty. So there are no free electron present here in the conduction band and the valence band will be having full of electrons and there is no empty state here. So here when an electric field is applied, the electrons which is present in the valence band will not be able to transfer to the conduction band, whereas the conduction band has an ample amount of free states but there is no electron present in it. So here it results in the insulator. So the next one is the semiconductors. So what happens in the semiconductor? The difference between the insulators and the semiconductors is quantitative. The difference is only in the magnitude of this band gap. Semiconductors are insulators with relatively a small band gap. That is, the forbidden energy gap will be small in case of the semiconductors, whereas the band gap will be large for the insulators. So at 0 degree Kelvin, the semiconductors will be acting as an insulator. So when an energy is given or at high temperature, a fraction of electrons can be found in the conduction band. So the resistivity decreases with increase in the temperature in the semiconductors. There is a Also, there is a qualitative difference between the metals and the insulator. The highest energy band containing electrons is only partially filled for metals. Thus, for good conductors, even for at low temperature, the resistivity arises from the electron scattering from lattice vibration and lattice defect. Vibration increases with temperature and high resistivity, and hence here the metal's resistance increases with increase in temperature, whereas for the insulators and semiconductor the resistivity will decreases with increase in the temperature. So as we discussed, there will be no difference between the insulators and semiconductors at low temperature. In either material, there are electrons in the conduction band, and so conductivity vanishes at the low temperature limit. As temperature increases, the electrons in the valence band of the semiconductor will be able to move to the conduction band, whereas in case of insulators, because of the large gap here, so the electrons will not be able to go to the conduction band, and hence there is no electric conductivity. The semiconductor silicon has a band gap of about 1.1 electron volt compared to 5 electron volt for diamond. The relatively small band gap of semiconductor allow for excitation of electrons from the lower band to the upper band by reasonable amount of thermal or optical energies. So at room temperature, a semiconductor with one electron band gap will have a significant number of electrons in the conduction band, whereas the insulator will have negligible number of such excitation. Thus, an important difference between semiconductor and insulator is the number of electrons available for conduction can be increased greatly in semiconductor by the thermal or optical energies. So the next topic what we will be discussing is about direct and indirect band gap. So we have the band structure of gallium arsenide, which has a minimum in the conduction band and a maximum in the valence band for the same value of K. So K is called as the electronic propagation constant, also called as the wave factor. On the other hand, silicon has its valence band maximum at a different value of K than its conduction band minimum. Thus, an electron making a smallest energy transition from the conduction in gallium arsenide can do so without changing in K value. On the other hand, a transient from the minimum point in the silicon semiconductor band to the maximum point of the valence band requires some change in K. Thus, there are two classes of semiconductor energy band, direct and indirect. We can show that in indirect transition involving a change in K requires a change in the momentum for the electrons. In the direct semiconductor such as gallium arsenide, an electron in the conduction band can fall directly to the empty state in the valence band, giving of the energy difference as a photon of the energy. So we can see the concept here with respect to the diagram. So here, this is on the other hand, silicon has its valence band maximum at a different value of K than its conduction band minimum. So the K value here for the valence band maximum is this, and the K value for the conduction band minimum is this. Thus, an electron making a smallest energy transient from the conduction band to the valence band in gallium arsenide can do so without the change in the K value. On the other hand, a transient from the minimum point on the silicon conduction band to the maximum point of the valence band requires some change in the value of K. Thus, there are two classes of semiconductor energy bands, direct and indirect. We can show that an indirect transient involving a change in the K requires a change in the momentum for the electron. In a direct semiconductor such as gallium arsenide, an electron in the conduction band can fall directly onto the empty state in the valence band, giving off the energy in the form of an light energy photon equal to which energy is equal to Eg h into nu. H is the Planck's constant. On the other hand, an electron in the conduction band minimum of an indirect semiconductor such as silicon cannot fall directly to the valence band but must undergo a momentum in the change in the momentum as well. The difference between the direct and the indirect band gap structure is very important for deciding which semiconductor can be used in devices requiring light output. For example, semiconductor light emitters and lasers generally made of materials capable of direct band-to-band transition or of indirect materials with vertical transition between the defect state. A direct band gap semiconductor is the one in which the maximum energy level of the valence and the conduction band will align with respect to momentum. In the direct band gap semiconductor, a direct recombination takes place with the energy equal to the energy of the light particles. So here an indirect semiconductor is one in which the maximum energy level of the valence band and the minimum energy level of the conduction band are misaligned with respect to the momentum, and due to the difference in the momentum is conserved by means of releasing an energy, and only after that both the momenta align themselves and recombination occurs with the release of energy. Here the example for indirect band gap is silicon and germanium. So in this module, we have discussed about what is metal, semiconductors and insulators. So this classification is based on the energy gap or the forbidden energy gap, the conduction band and valence band occupancy. Next, we have discussed what is meant by direct and indirect band gap. So in the next module, we will be discussing about the intrinsic and extrinsic semiconductors. Thank you.